It's my pleasure to introduce Ted Spears from Microchip. They had made a major architecture announcement at the summit in December, and I will turn it over to him for his presentation.
All right, can you guys hear me? All right, yeah, so as Ted mentioned, my name is Ted Spears, and my, we have bouncers, can we? My role at Microchip is to define our FPGA roadmap, and I'm also on the RISC-V Foundation Board of Directors. And today I'm going to, as Ted mentioned, we did an announcement at the last summit, and I'll talk more about it, the PolarFire SoC, a secure, low latency, heterogeneous compute platform for the edge. So I wanted to start with some goals and messages I hope that come across today. First, hope to teach you or inform you on why our FPGA technology matters at the edge. I think that's important. We're not that well known yet in the FPGA space. And then also, it was kind of a lighthearted part, but a historical perspective here. We've been involved in RISC-V for a long time, and talk about our BU's involvement in RISC-V. And then finally, what PolarFire SoC can do for you. All right, so we actually saw a slide that looked a lot like this today at the opening keynote. This is kind of the framework for compute today. So a computer is really kind of this one entity that spans the globe. On the right there, you see the data center and the cloud, and then on the left, the device and sensors and actuators. They're kind of like the nerve endings, and in between, we have gateways and transport, kind of the nerve connecting these two things together. So this is a framework that I use to digest or understand what's going on in compute. So there's some megatrends at play that are kind of forcing how this all emerges, including exponential growth of connected devices and human machine out in the device domain. And then like moving over to the right, all those devices are creating massive amounts of data for the data center to process in the cloud. And it leads to the more going on today in the compute domain in the middle there. So we've been promoting low power for a long time, actually, but the only people who cared about it for the longest time were cell phone. But now power used to be like a first, maybe a second order concern by the customers, but now it's really a zero order concern. There's nothing I've known that make a customer switch from a competitor to us other than power. So it's a lot to do to get something to switch. So that's why I call power a zero order concern. So power kind of manifests itself differently as you move across the chart, and depending where you are in the device, you're constrained by some low amount of power, either a small battery that has to operate for 10 years, or maybe something more moderate like power over Ethernet. Over to the right, the data center. You got this massive structure, massive investment with a fixed power supply going into it. That power is actually the main cost of your data center, and you want to get the most utility out of that data center. And in the middle there, that domain, the equipment that resides here is often in a hostile environment outside, no fan provided. So this fanless enclosure, their power is a heat problem. It's not a power amount problem or a power cost issue. It's like I can't get the system to work because too much heat that I can't get rid of. So solution trends, starting with, as we all know, compute now is being moved from the cloud, over to into the edge or into the gateways and into the edge. That solves two problems at least, latency being one of them, but also lowers the cost of your system if you can do a lot of the compute out at the device rather than ship it all the way back to the cloud. Also, this is now a huge attack surface, connected attack surface, and so it's vulnerable with all these devices. So hardware security is important if you're going to want to kind of defend that attack surface. And then safety and reliability needs are increasing as well. That's got to do with the human interaction dimension of all this. All right, so now we have what the one and only edge, or the edge, is defined by Wikipedia. Right, this is the Wikipedia basically defines anything that's not done in the cloud is edge computing. So everything done in the gateways and transport domain or in the device can be considered edge computing. All right. Excuse me. But is that really the one and only edge? This is not a Rorschach test, but anyone know what that might be?
It's like a dog.
Yeah. Pikachu, maybe? I don't know. But so some context. This is Galaxy GNZ11. This is the farthest known object that's ever been observed. It's about 13.4 billion years, at least when the light that we're seeing now, it was 13.4 billion light years away. So that is the edge of the universe. Moving closer, what is this? It's an eclipse of the moon and the sun. So actually, that's the planet Pluto, or I guess not a planet, I don't know what you call it now, planetoid. And that's actually the sun going through the atmosphere of Pluto, and this is imaged by the New Horizons spacecraft as it flew by Pluto in 2015, the edge of the solar system. All right, so this is a cool app from Flight Radar 24. These guys track 200,000 flights a day with this application. You could download this and see all those planes. You can actually see them moving in real time. It's not static, but 200,000 flights a day are being tracked by Flight Radar 24 at the edge of the Troposphere, where all these planes are flying. Zooming in a little bit, you can't even see Switzerland. There are so many planes, big yellow planes above us right now. So what's the common denominator? It's really, microchip FPGAs at the edge. So airplanes, 787 Dreamliner. We're, that New Horizon. We were on the instruments. We were on the flight control systems, the New Horizon. And then, that we didn't quite make it ourselves to the edge of the universe, but the instrument, the Wide Field Camera 3, was installed on the space shuttle, or the space telescope in 2009, was Microchip FPGAs. So really, we dominate from the edge of the atmosphere to the edge of the solar system, and that New Horizons eventually will be the edge of the heliosphere. So our FPGAs dominate the space market, and the edge of the troposphere, about 30,000 feet. Any plane you get on, there's those 200,000 planes in the air. There's probably 100 to 1,000 microchip FPGAs on there, controlling engines, controlling doors, controlling flight panel displays. So used extensively in this market. So it really comes down to, this is like a reliability need, and in the case of the airplanes, the enemy is the high energy neutron. They exist. They're in the room today. They're hitting you right now, but there's even more of them at 30,000 feet. These are created by cosmic rays in the upper atmosphere, and they can change a state of an SRAM from a 1 to a 0, or in the case of an SRAM-based FPGA, your AND gate becomes an OR gate. That's not very useful if you want to move 200,000 planes every day from point A to point B. So our parts are immune to these type of effects, and then going up in space, we're actually immune to the cosmic rays there and other things that might switch an FPGA state. So that's why we gain traction in this kind of reliability segment. All right, so we also have developed, we're leading edge security technology that actually leverages our non-volatile technology. So our wafers, when they come out of the fab, the first thing they see from their perspective is an HSM that's like injecting keys into them. So we start injecting key material into our FPGAs uniquely into every single part that's manufactured, and it's injected by an HSM. So there's no human involved in the creation of these keys. It's all securely stored in hardware security. So as we move through the process, the life cycle, final test, we can do, when we test it, we actually take a certificate that says this chip was tested by Microchip and meets these specifications. We'll sign that with our key and install that certificate in the Microchip FPGA. So now you have the basis of something that you can actually secure your supply chain. So the customer can actually use HSMs, and we provide ways for them to secure their supply chain. Then on top of that, build secure applications into our FPGA. So finally, power. This is a plot. I do kind of a Monte Carlo, lots of different compute workloads represented by each dot. And on the x-axis is PolarFire. That's our latest FPGA. And I clipped it at 8 watts. So that's the PolarFire power on the x-axis. And competitor power on the y-axis. And so you see above 8 watts there, more than 50% of the dots are, for the competitors are well above 8 watts. And, I call 8 watts the edge of pain. There's no magic number about this, but people designing systems, these fanless enclosures, life just gets more and more difficult the more power there is on each individual device on the board. It's not a problem getting power to the system, it's a problem removing the heat, and 8 watts is a pain threshold that is meaningful. And so, competition at 8 watts is on average, 4.5 watts for our device. So we actually enable capability in these fanless enclosures that you cannot do with competitors. So kind of back to this framework, you see low power is important, security is important, reliability continues to be important. And, this is where we're targeting our FPGAs in this domain. So the fanless enclosure is really a sweet spot for our FPGA technology. And then a little bit in the device domain, especially we'll talk about cameras later, but those are controlled by, limited by something like power over Ethernet. All right, so now I'm going to, I was inspired by GN-Z11, and we'll start using some cosmology analogies. So if anyone is an expert in general relativity, don't check my math. I'm a rookie here, but shifting from red to blue, that galaxy GN-Z11 is moving away from a sort of high rate of speed. So the reason that we know it's far away is because it has the largest redshift ever observed. And so that light that's here is 14 billion years old or so, but it's actually now 39 billion light years away. So everything redshifting is diverging, shifting away, being driven apart. And the converse of that is the blue shift, and that's things that are converging, moving towards each other. So in March 2010, we shipped the industry's first SoC FPGA, and people can quibble this, but by that I mean an FPGA that has a microprocessor or controller subsystem with a full set of peripherals and a standard interface to the FPGA. There's many ways people tried to create such an animal before, but this is the first SoC FPGA with this basic architecture, which is kind of the de facto architecture of SoC FPGAs. And ours was microcontroller-based, Cortex M3, and we, in October 2012, we announced SmartFusion 2, which was an extension of this technology. So this got us into, we were in our own space, security and reliability, literally space, but we were taking steps into kind of the mainstream compute with a product like this. But it seemed like we were still in a red shift. We weren't getting closer to what the market needed with this type of product. So there was some unseen force creating this red shift, driving us away from the mainstream compute. And what that unseen force is basically Linux. We were defining those original products back here. This is the total market size, relative market size of Linux in red here, and real-time operating systems in blue. When we were defining these things, they were roughly the same size, but Linux is just growing adoption at a faster rate. It's an ease of use prospect. Engineers wanted, the ability of Linux to develop their systems quickly, and we were not satisfying that need for Linux, and that was what was driving us apart. All right, so this is an actual calendar entry from Outlook on my calendar on December 11th, 2014. And had one meeting in the morning, a phone call with a company called Brunspace. And meeting was pretty normal until maybe about 9:55 when went to 10:30. So about 10:25, the customer mentioned that he was using one of our FPGAs with a soft core that was running Linux. We didn't support anything like that. We had a Cortex M1 from ARM as a soft core that didn't support Linux. I said, well, what are you using? He says, well, there's something called a RISC-V. Go check it out on their website. So at 10:31, I found RISC-V.org. In 10:32, I was telling everyone, people about it inside my company. And I think at 10:33, I was telling people outside of my company, have you looked at RISC-V? So, December 9, 2014 is when our world turned blue, and we started converging with the rest of mainstream FPGA market, or compute market, let's say, with RISC-V, our discovery of RISC-V. I think I'll go through some reasons why our world turned blue, but I'll just observe that a lot of people's life turned blue when they discovered RISC-V. So there's people doing safety now, kind of operating in their own domain, people doing security, doing research, but no way to implement it, people doing formal verification, formal methods, formal specifications, all the interesting work that's being done, but this, their world turned blue. They're now converging around RISC-V. In our case, things quickly started happening where we actually had a satellite customer that quickly needed a processor for an FPGA that was going to go in space, and we had no way to meet their needs. It didn't meet the Cortex M1. So we happened to know at that point people from Sci-Fi, and they came in and delivered us, met the customer specs, with agile methods very quickly, and that has since turned into $1 million order for us for a soft processor in space. So I think one of the messages from Callista is, it's business at the end of the day, and this has represented, this blue shift did turn into real business for us already. All right, so I talked about this slide, the Linux adoption, why it's adopting. Just started talking about, one of the real-time applications that we couldn't solve with the M1 is people doing like motor control and industrial. They had, latency requirements, they had jitter requirements, interrupt jitter tolerance requirements to control their motor using an FPGA plus a processor, but they also wanted to run their displays and their application on Linux, and they couldn't get that done in a single device. And so we wanted to figure out how to solve that problem, and so we engage with Sci-Fi as can we make a device that solves this problem. Customer runs Linux, but also gets their real time. So last summit, we announced this RISC-V, or PolarFire SoC, which has this whole RISC-V subsystem on there. It includes 4 application processors from Sci-Fi, as well as a monitor core, which I'll talk about later. So it's important to note this is a hardened RISC-V subsystem. I'm not talking about a soft core that you can program in an FPGA. This is a hardened SoC FPGA. And those 2 partners, one just Sci-Fi that actually contributed to the development of this. UltraSoC is also a partner creating the trace on this device. So more POs being written by Microchip for RISC-V. So zooming in a second, in the deterministic L2 memory subsystem and coherent switch, we we showed this at the summit last year, but basically, this shows the responsiveness of these 4 processors doing symmetric multiprocessing. Linux would be an example, and how they respond to an interrupts service routine. And this is kind of mapping of the execution time. And that jitter there, not acceptable for the people doing the motor control. So with Sci-5, we said, well, let's take this subsystem and architect it so that one or more of the processors, we can convert the L1 cache to a tightly integrated memory, and the L2 we can partition as much as we want for additional loosely integrated memory. And with some other innovations, we've actually got this jitter down to pretty much 0. So you can be running Linux over here, but you're got guaranteed execution on your real-time application running on the other core. And then, of course, you can further repurpose the L2 cache to pass messages between these two domains. So, looking a little bit at this part of the device, we have some 128K bytes of boot flash on the device. So when you couple that with the flash that's on all our FPGAs, we store a 0-stage bootloader in the PolarFire system controller, which has a crypto processor. That encrypted image of 0-stage bootloader is decrypted and certified, pushed into the monitor core, which then does the same on a first-stage bootloader that you can store in the 128K bytes of PolarFire SoC. So we see a lot of applications, edge applications, and we're seeing a lot in this area we call secure embedded vision. Basically, cameras, lots of cameras, different configurations of hardware, heat-constrained environments, needing to control something, like a drone. There is often real-time control needs, so this is an exploding market where we see a lot of excitement for PolarFire and PolarFire SoC. So we've announced, 2 ways, you can start developing today. I think people are probably familiar with a Hi5 Unleashed expansion board and Hi5 Unleashed. Put them together, and that's basically PolarFire SoC that's going to be coming out early next year. And then Antmicro has produced a virtual platform called Renode that is open source and can run code, RISC-V code, as well as you can run accelerators, emulate accelerators that are going to be put in our FPGA. So you can get started in hardware or software today. We've invested a lot in the ecosystem. So we have this ecosystem called My5, and boards, CPUs, operating systems are all part of this ecosystem. And there's a lot of partners, and we're actively looking for more people to help make this a really robust launch and have everyone participate in RISC-V and get down to the business of making money. So finally, the recipe for the new golden age. So Dave Patterson and John Hennessy won the Turing Award, and the title of their Turing talk was A New Golden Age of Computer Architecture. And they highlighted 4 areas: like open instruction sets, enhanced security, agile chip development, and domain-specific hardware, software co-design. And I think today we've definitely, as our world shifted from red to blue, we've already embraced fully the first 3 of these things, and just stay tuned for what's happening next. Thank you.
We have a minute. If any questions for this TED?
Yeah, happy to talk to anyone about PolarFire SoC. There's lots of people who can talk to you about PolarFire SoC. We have an exhibit, but also, with my RISC-V hat, how you think things are going in the foundation. I'm always happy to talk at length about RISC-V, what we can do better, ideas on how to grow it and make it even more fantastic. Thanks again.
Thanks, Ted.